Hi, Physics 2. Mr. Janowski here. This is part 6 of the chapter 36 slides, and I want to teach you how an electric motor works, but I realized that will make a lot more sense if we go back and do a piece of physics that I would have loved to have taught you last year, but there wasn't enough time. So we're kind of taking a detour from Physics 2 stuff, and we're going to do something that really properly belongs in Physics 1. Um, but it's useful. And as you go on to study physics in college, you're going to want to have learned this. So it'll be good. You'll enjoy this. I like this stuff. So let's get started. So, from last time, what is a long wire with many turns called? That is called a solenoid. And we learned a formula for figuring out the formula for a solenoid, the formula for the strength of the magnetic field in a solenoid. And turns out it is proportional to, well, this constant, but also the current I going through it, and the number of turns in the solenoid, and the magnetic field is inversely proportional to the length of the solenoid. So what do you get when you put an iron core inside of such a device? You get a electromagnet. So this will be useful when we start talking about motors, of course. But again, first, we're taking a detour. So back to Physics 1 stuff. Alice, Billy, Charlie, and Denise are each trying to loosen a bolt. They take turns grabbing the wrench and applying a 100 Newton force. So who is going to have the most luck? So look at this picture, think about it. Which one of our four favorite physicists is going to have the most luck at loosening this bolt? And the answer is, I'm not telling you yet. We'll get there in a couple of slides. So, what is the most important thing you learned in Physics 1? You better have memorized this by now. The most important thing you learned in Physics 1 is Newton's second law, F equals ma. And if you're being real precise about it, it's sigma F equals ma, where F and A wear hats. And this is Newton's second law for forces. Well, it turns out there's also a Newton's second law for torques. And that one is tau equals I alpha, or sigma tau equals I alpha, where tau is torque. It's not current in this case, so it's going to get a little confusing. I stands for this thing called moment of inertia, more on that in a couple of slides, and alpha is angular acceleration. So force and torque are cousins. So let's look at F equals ma and think about what that means. F is force, m is mass, and a is acceleration, and those are the units. So forces accelerate masses. That's what forces do. Torques angularly accelerate moments of inertia. So tau is torque, I is moment of inertia, and alpha is angular acceleration. And the units for these guys, the unit for torque is Newton meters. The units for moment of inertia is kilogram meters squared. That one's a little bit weird. And alpha, the units for that are radians per second squared. So what are these things exactly? Well, again, look at Newton's second law for forces. Forces accelerate masses. Mass, focus on the M, it's a measure of inertia, and inertia is laziness. So if you have a large mass, you don't want to accelerate, which means you don't want to change your straight line motion. So this should make sense. If you look at that formula and think of what happens if M gets big or small. So if you put a force on a small mass, it will accelerate a lot. Now let's go down to the Newton's second law for torques. So tau equals I alpha. So what exactly is I, moment of inertia? It's the cousin of mass, and it is also laziness. It's more complicated than mass. It's proportional to mass, but it also greatly depends on how the mass is distributed. There's a whole lot of formulas and integrals you can do to figure out what the moment of inertia for a thing is. But unfortunately, we didn't have time last year to do it, and we're not going to go into it that much here. But basically, I is the cousin of M. It is also laziness. If you have a large moment of inertia, you don't want to angularly accelerate, meaning you don't want to change your rotational motion. So that means if you have a large moment of inertia, it will take a very large torque, tau, to get you to angularly accelerate, alpha. You don't want to start spinning, you don't want to stop spinning, and you don't want to change the way you're spinning. That's what it means to have a big I, moment of inertia. And again, just to be clear, I in this context is not I for current. It is I for moment of inertia. So another formula for torque. Torque is the cross product, also known as the vector product, of what's called the lever arm and the force. So R, sometimes it is the radius. We use R for the symbol for the lever arm and the force. So what exactly is lever arm R? It is the distance from the pivot to where the force is applied. So the pivot can be different things. If you think of a bicycle wheel spinning around its axle, well, the axle is going to be the pivot, and the distance away from that, so if you grab the wheel all the way on the outside and spin it, that is your lever arm. If you reach halfway through and you're trying to turn this bicycle wheel by the spokes, that is your lever arm, your distance from where you're applying your force back to the axle. If you're thinking about kids on a seesaw, well, your pivot would be the fulcrum of the seesaw, and your lever arm would be how far away the kids are sitting from the fulcrum. So tau equals R cross F is really the vector version. We can also use just this kind of scalar version where we're only interested in the magnitudes, where we get the magnitude of torque is equal to the magnitude of the lever arm times the magnitude of the force times the sine of the angle between them, where theta is the angle between them. So let's think real quick, sine of theta. How does sine of theta behave? What is sine of theta when theta is 0? Well, sine of 0 is 0. What is sine of theta when theta is 90 degrees? Sine of 90 degrees is 1. And that's the biggest this is going to get. 90 degrees is going to get you the most torque, it turns out. So, nice graphic here. Torque depends on three things. It depends on the magnitude of the lever arm, so how far away from the pivot the force is being applied. It depends on the magnitude of the force. Well, that makes sense. The bigger the force, the more torque you're likely to get from it. And the sine of the angle between them. And by convention, torques that will cause the thing to turn counterclockwise are going to be considered positive, and torques that cause clockwise rotation are going to be considered negative. So remember, when we're doing x's and y's, left is negative, right is positive, down is negative, up is positive. Well, when you're doing torques, counterclockwise is positive and clockwise is negative. So the exact same idea there. And well, before I get to this one, also think of the right-hand rule. So just a quick lesson in how the cross product works. So the right-hand rule for cross products, we're doing like, we know the one formula that has, it has an L cross B. So when you do the right-hand rule, so hold out your right hand with your fingers extended and your thumb at right angles to your fingers. When you do the right-hand rule, the first thing is your thumb, and the second thing is your fingers. So it matters when you're doing cross product. Regular multiplication is commutative. So, x times y is equal to y times x. Well, it turns out that when you're doing cross products and vectors, that's not true. They're not commutative. So r cross f does not equal f cross r. It turns out that r cross f actually equals negative f cross r, but that's not the point. So when you're trying to figure out the torque, first do the r, that'll be your thumb, then do the f, that'll be your fingers, and the direction of the torque is the direction your palm is pointing. So if we're looking at this thing, this graphic here, so this is the pivot, this is where we're applying the force, and we're applying it this distance r, this lever arm r away. So you think about the way this thing's going to spin. This thing's going to spin counterclockwise, and it may be a little bit surprising that the direction of the torque is a vector. It's not going around and around. The direction of the torque in this picture is basically just up. This is pointing up. So that's the way we indicate torque and its direction for mathematical reasons. Seems a little bit weird, but it works. So now back to this do now question. So we have Alice, Billy, Charlie, and Denise. They're each trying to loosen the bolt. They take turns grabbing the wrench and applying 100 Newton force in the directions indicated by those arrows. So who is going to have the most luck? So you can either rely on your experience working with wrenches and screwdrivers and such, or you can rely on the math. So here's your formula for torque. Torque is equal to magnitude of torque is equal to magnitude of R times magnitude of F times sine of theta. So the answer to this, give me just one more second to think about it, is Charlie. Charlie's going to have the most luck. So all four of these people are exerting the same force. So F in all of these cases is going to be equal to 100. Now let's look at Alice. So Alice is doing 100 newtons of force, but her R is going to be, the R is going to be 0. So in this little formula here, the A is not for Alice, A is for applied. I should probably change what that says. I think I will. I'll go back and change it. Alice, 100 newtons. I've also written this in the other way. Oh, well. Alice has a force, but her lever arm, which is also sometimes called moment arm, but her lever arm is 0. So Alice does no torque. Billy has a force, and his lever arm is not 0, and the angle at which he's applying it is 90 degrees. So sine of 90 is 1. So he will get some torque. He might have a little bit of luck turning this, but let's see if we can do better than him. So skip Charlie. Let's look at Denise. So Denise has a big lever arm. She also has a big force. However, sine of the angle between the lever arm and the force, that angle is 0 degrees, and sine of 0 degrees is 0. So Denise is not going to get any torque. She's just going to pull this thing straight sideways. It's going to come right off this. And if this were a closed wrench, she would be pulling on the nut sideways, but she wouldn't be turning it at all. So Charlie's going to have the most, because Charlie has a big lever arm, and he has the same force as everyone else, times sine of theta. Well, he is exerting his force at 90 degrees to the lever arm, and sine of 90 is 1. So Charlie's going to have the most torque. He will have the most luck loosening this bolt. So another example of this. So I wish we were in the classroom, for a number of reasons. But one is, that door that we have. This is a great example of torque, and something that you deal with kind of. You see this a lot, actually. Anytime you try to hold the door for somebody, and the door has an automatic closer, this comes up. So think of this. So out here, this would be the hallway out here to the left, and then you walk into room 321, and we're in here. So this is our door. There's a door closer, which I've kind of simplified how this works here. But there's a door closer, and we're looking top down at this. So that's how this works. So there's the wall. There's the wall. Here's the doorway. Okay, you can read this picture. So the door closer. So that little powered thing that pulls the door closed. Well, it's pneumatic, whatever. We're going to say it exerts a force of 100 newtons at a distance 0.30 meters, so 30 centimeters away from the hinge, which is about a foot. So the torque that this caused is given by this formula. So I should have switched this back. Whatever, it's fine. And we're going to say, I know it doesn't look like it, we're going to say that the angle at which the door closer is causing its force is 90 degrees. I know it doesn't look like this in this picture. This picture is greatly simplified, but whatever. Anyhow, the point is the door closer is causing the door to go clockwise. It's causing this negative amount of torque. So if you want to keep the door from closing, so we're going to have Alice and Billy try to keep this door from closing. They're each going to go out there and they're going to apply forces on the door, but they're going to apply them at different distances from the pivot. So they're going to have different lever arms here. So let's look at our formula for torque. And you can see that the amount of torque each one of these people is going to get depends greatly on their lever arm, how far they are from the hinge. So in order for Alice to generate the 30 Newton meters of torque she needs to keep the door from closing, remember the door is doing negative 30 Newton meters of torque, and she's this distance away, so 9/10 of a meter, 90 centimeters. We're going to figure out how much force she needs. So it turns out she doesn't need very much force at all. She only needs 33.3 newtons of force, which is only about 7.5 pounds of force, and this is very doable. It doesn't take a whole lot to hold the door if you're holding it far from the hinge. Now let's look at Billy. So Billy also needs to make 30 Newton meters of torque to counteract the negative 30 Newton meters of torque that the door closer is doing. But he's only a centimeter away. So he's going to try to hold the door right there. So how much force does he need? Well, he needs, plug this in, solve it for F, he needs 3,000 newtons of force. Alice only needed about 33 newtons. Billy needs 3,000 newtons of force. So this is about 637 pounds of force. So this is very difficult. So I don't know if you happen to have, maybe the screen door at your house or whatever has a door closer. If you're interested, you can go out there and try it and see why this works. If you hold the door open and you're holding it far from the hinge, it's very, very easy to do it. If, on the other hand, let me clarify that. If you're far from the hinge and you're applying it at a good angle, so if you're applying it at about 90 degrees, it's very easy to do it. It doesn't take a whole lot of force. If, on the other hand, you open the door and then go walk and touch hold the door, but very close to the hinge, and see how much more force it takes to keep the door from closing on you. It takes a lot here because your lever arm is very, very tiny. So the angle also applies. This is why if you've ever tried to hold the door for the person and you stand way out of the way and you're holding it at a weird angle and you're not getting very good leverage, basically, not basically, exactly, you're not getting very good leverage, it's very hard to hold the door. So a famous ancient Greek once said, "Give me a lever and a place to stand, and I will move the earth." This was Archimedes who said this. So yeah, Archimedes is the Eureka guy. He discovered the principle of water displacement and invented Archimedes' screw for lifting water and things like that. But yeah, he said that. So what did he mean by this? Well, if you look at the formula for torque, you can get a lot of torque even with a fairly small force by making your lever arm very big. So he knew that if he were able to somehow stand way out there in space with a giant lever, he certainly knew the Earth was round. Only idiots think the Earth is not round, and he knew that the Earth was round. Everyone does. He knew that it wouldn't take a whole lot of force to get a lot of torque out of this. You just need a giant lever arm. So probably a little impractical to actually do, but yeah, he knew how this worked. So yeah, when you talk about leverage or leverage, or mechanical advantage, you're usually talking about torque. That's what mechanical advantage is in most situations. So where else do we see torque? It comes up a lot. So look at the top picture. This is how your bicep works. So humerus coming down here, radius and ulna coming down here. So your bicep, if you can imagine standing straight up, holding your arm out at a right angle in front of you like this, and you're going to curl a dumbbell or something. So the dumbbell, the load out here, this weight is going to cause a torque that's going to try to bring your arm down. And the way we're looking at this would be clockwise. So this would be a negative torque. And what's happening inside your arm? Your bicep is attached, not exactly at the pivot, because then it couldn't do anything, but it's attached a little bit in front of the pivot. So your bicep contracts and pulls up here. Meanwhile, the weight that you're holding is pulling down here, and that's how you make a torque. So basically all the muscles in your body work, with the exception of your heart and maybe your stomach muscles and things like that. Not your abs. Your abs are doing torque, but the lining of your stomach, the smooth muscle, whatever. I don't care about anatomy. Basically all of your skeletal muscles, I should have said that, all of your skeletal muscles work on torque. They're going to apply a force some distance away from a pivot and they're going to generate a torque. So also, kids on not a merry-go-round. What's this called? Oh my God, the word's escaping me. Seesaw. So, yeah, it's a seesaw. So how does this work? You can have two different sized children. So we have a smaller, younger child here and a bigger, older child here. So she's got more mass. So her weight coming down is a force here. He has less mass and less weight, so he has less force. But if he stands or sits far enough away from the fulcrum, he can exactly balance the torque that she's creating. So that's how that works. If you're making a mobile, something like that, you can apply. So this is kind of a complicated thing because there's two different stages going on here in this mobile. But yeah, there's a string coming down. So this would be our pivot. And as long as the total force down here times this radius or this lever arm is equal to this force times this lever arm, yeah, the mobile will be balanced right there. And down here, if you ever see, if someone's hanging out a shingle, is a way of saying it, they've got a sign hanging out from a wall, there's torque going on with this. So there's a whole bunch of physics problems that if we had had more time in Physics 1, I would have taught you them. They're called statics, how to do these problems. So yeah, back to this slide. If something has angular acceleration, one more example of torque that you don't see here. You commonly hear torque in the context of cars. If people are rating cars, they talk about how much horsepower it has, and they also talk about how much torque it has. So torque is basically the ability of the car to angularly accelerate the tires, to get the tires to rotate. And more torque can make the tires angularly accelerate faster. So that's that. Now back to this slide. So Newton's second law for torques. If something has angular acceleration, if something is starting to spin, or it's changing the way it's spinning, that means there must be a torque on it. And the flip of that, so this is actually basically Newton's first law for torque. If something has no angular acceleration, there must be no net torque on it. So if sigma tau equals I alpha. Well, if alpha is 0, then the right side of this, or I guess the middle part in this one, is equal to 0, which means the sum of your torques must be equal to 0. So Newton's first law, the way we've learned it before, is an object at rest or in motion will stay at rest or in motion unless acted upon by an outside unbalanced force. So that is saying sigma f, if sigma f equals 0, then A equals 0. Well, same idea with torque. If sigma tau equals 0, then alpha equals 0. So if there's no net torque, it won't angularly accelerate. And if it's not angularly accelerating, then that must mean there's no net torque. So yeah, here is the top one here, Newton's second law for torques. And this bottom one, this idea, is basically Newton's first law for torques. So to review, what is the most important thing you learned in Physics 1? No, it's not the bloody cheetah, Malachi. It is, in fact, Newton's second law for forces, F equals ma, or the fancier version, sigma F equals ma, where things wear hats. So what is the new version of the most important thing you learned in Physics 1? It is Newton's second law for torques, tau equals I alpha, or sigma tau equals I alpha with hats. So what three things does torque depend on? Torque is going to depend on, well, let's look at our formula for it, R, F, and theta. So R is the magnitude of your lever arm, how far away from the pivot you're applying your force. It's going to depend on the magnitude of the force. More force will get you more torque, all else being equal. And it will depend on the sign of the angle between them. So the way to get the most torque is to apply your force at a right angle to your lever arm, your moment arm, the thing that's connecting your pivot to where you're applying your force. And again, in general, torques that cause counterclockwise or anti-clockwise rotation are considered positive, and torques that cause clockwise rotation are considered negative. So left and down and clockwise are negative. Right and up and counterclockwise are positive. That's how this works. And the symmetry mathematically between these ideas and left and right and up and down, to me, is just beautiful. I love this stuff. That's it for this part. A lesson that properly belonged in Physics 1, but there wasn't time. So we're going to take this idea. Having learned this is going to make what we're going to learn next, which is understanding how an electric motor works. It's going to make that much easier. So hopefully you found that interesting.